welcome everyone to our course. Today we are having the 6th week lecture. So, if you remember last week we have started with perovskite solar cell. Now, perovskite solar cell, as we have learnt, they provide us some of the advantage over the organic solar cell and also the dye sensitized solar cell. Like if you remember, some of these excellent properties which we have discussed in the last class is that this perovskite material has a tunable band gap. That means the same material, by changing either the cationic component or by anionic component or by the metal ion, we can tune the band gap over a wide range. Now, this tuning the band gap actually tells a lot about the system, because if you can tune the band gap, basically you can tune its absorptions. So, in the same material, starting from the UV to visible to near IR, the absorption is possible now. The next important thing with this material is that this kind of material has a very large absorption coefficient. So, we do not need to make a very thick film for enough amount of light absorptions in the active layer. Moreover, the processing cost of the perovskite is lower in comparison to the other third generation technology. Perovskite solar cell can be fabricated by a solution based approach, where you can take the precursor molecule in a good organic solvent and then you dissolve it and then make a thin film out of it. You can tune or control the properties of this thin film. Similarly, this perovskite material, they have a large band gap variations simply by morphological variations of this structure. They show a temperature dependent crystal structure orientations. So, because of all of this thing, or because of this all excellent optoelectronic properties, it was the material of choice for solar cell devices. And we have seen from the efficiency graph that only within 5 to 6 years of research, starting from a decent 3.8%, the efficiency raised to 15% until 2015, and the present number of efficiency is 22% today, and this number, as I mentioned, that increasing every day. Now, in the last lecture we mentioned that we will learn about how to fabricate a perovskite solar cell, or what are the different components of a perovskite solar cell. In today we will see that what are the different kind of geometry possible in this kind of solar cell, or how you can make the perovskite solar cell in the lab. Let us take a look on the device structure. The device structure, related materials and interfacial modification are key factors in performance of solar cells. So, obviously, like as I say that this efficiency in a solar cell is a product function, it depends upon exciton generation. Now, this exciton generation comes from the choice of material. If we have a material which have a low band gap, then that material can absorb the light in the near IR range. So, the related materials is very important. Interfacial modification. Now, when you make a device, so a device is a sandwich structure where you put an active layer between the cathode and anode. Now, many times very often you put blocking layers, either an electron blocking layers or hole blocking layer, to allow one particular kind of charge carrier to diffuse over the other. Now, so this interface modification plays a very important role in determining the VOC and the fill factor of the devices. So, all of these parameters needs to be optimized for devising a optimum performance of a solar cell. Two typical structures can be constructed: mesoscopic structure and planar structure. Mesoporous TiO2 layer usually is used to collect the electron. Organic hole transport material, which you abbreviate as HTM, they collects the hole. Planar structure has simpler structure and high efficiency. So, people have fabricated either a mesoporous nanostructure, where you make a mesoporous layers with lot of pores inside the material, or one can make a planar structure where there is no corrugation or no porous structure in the material. Now, both of these structures have been tried in either PIN or NIP geometry and gives a different number of efficiency. Now, what is PIN and NIP geometry? These are the two very commonly used structural configuration in the perovskite solar cell. So, in the PIN geometry, what happened here, let us say, let me draw this thing. This is your ITO, which is coated on a glass substrate, and then on the top you have your metal electrode, right. So, this is your metal electrode. Now, you allow the light to pass through here. So, one can put the active layer of the perovskite here. This is your active layer. Now, I can put either titanium dioxide as an electron collection layer at the interface of the ITO and perovskite, and some hole transport material like any conducting polymer, for example, P3HT, as a hole collection materials at the interface of the perovskite and metals. So, then TiO2 is a N type semiconductor and P3HT is a P type semiconductor. So, between that I can think about an intrinsic layer of perovskite has been sandwiched. So, this kind of geometry is called NIP geometry. On the other hand, let us look the other figure. You have the same ITO here, which we have deposited on the glass substrate, and we have this top metal electrode. This is metal electrode, light is falling from here. In between I have a sandwich layer of perovskite. Yeah, one important thing to mention here. So, again I can put two different blocking layer or charge collection layer at these two interface. If I put some hole conducting layer like P dot PSS, and on the top if I put something an electron collection layer, like a common example is a small molecule spirometad or doped spirometad. This is a small molecule which conducts the electron. So, here I have a P type layer, I have an N type layer, and the intrinsic semiconductor is sandwiched between them. So, now consider there are two different geometry, one is PIN and another is NIP, or I think it is other way round. This was NIP, this kind of configuration, and here what we have drawn is the PIN. So, in NIP geometry we put a titanium dioxide layer at the interface of the ITO and the perovskite, and as a hole collection layer we use the P3HT, or you can use any hole transport material, any conducting polymer which has a very large hole mobility. Now, this TiO2 layer can be a mesoporous TiO2 or can be a planar structure TiO2. On the other hand, in the PIN geometry we put a P dot PSS, a conducting polymer layer at the interface of the ITO and the perovskite, and we put an electron collection layer, for example spirometad, which is a small molecule at the interface between this perovskite and the metal contact. So, now in either of these two cases we will get the JSC, VOC and fill factor. In both of these cases we will get J short circuit, VOC and fill factor. Now, if we calculate the IV curve in the NIP geometry of the same perovskite material, and if I plot the IV curve for the efficiency measurement for the same perovskite material, let us say CH3 NH3 lead iodide in the PIN geometry, what we will see that if we do a voltage sweep from the negative to the positive voltage and comes back from the positive to the negative voltage, in ideal case both the curve trace should be the same. So, what I am meaning that if I have a current versus voltage graph like this, and let us say this is an arbitrary example, although IV curves does not follow like let us say like this way. So, if the current or voltage graph follows like that when I do a voltage sweep like that, and then again if I comes back, so in ideally it should follow the same curve like this. So, ideally it will trace back when I sweep back the voltage from this one to this one and then back to this point. But in realistic case what happens, it does not trace the same path, but it deviates from the path a little bit, and this phenomena is called, this deviation from the original path, that phenomena is called hysteresis, and this is an intrinsic property of the perovskite material. You remember when we discuss about the barium titanate or calcium titanate, and I said that in the earlier days the perovskite was mainly used for its good ferroelectric properties. So, perovskite shows a ferroelectric properties. Now, in ideal case, once I want to make a device, I do not want to have any hysteresis in my device. Now, it has been observed that between this PIN and NIP geometry, one of the geometry, let us say PIN geometry, shows a better hysteresis or less hysteresis. Better hysteresis means here the less hysteresis in comparison to the NIP structure, although the reason is not very clear. So, if you do not want to have a lot of hysteresis in the circuit, so then we will prefer the PIN geometry over the NIP geometry. Now, you might ask, like, what we are so much concerned about the hysteresis, or what physical interpretation of the hysteresis. So, basically later on we will see that hysteresis can be related to the stability of the devices. Now, one of the major problem of the perovskite, although its efficiency is very high, is its stability. Now, this perovskite material, they are not very stable in the ambient condition. So, that is why we need to have a very controlled environment, like we need to control the humidity level and the oxygen level while fabricating this device. Now, once you bring this device outside this controlled environment, then its efficiency drastically drops. Now, what is the reason behind this? One of the reasons can be thermal degradations, one of the reason can be moisture sensitivity. So, these all of the reasons which actually makes this device efficiency very unstable. Now, apart from this factor, like this temperature degradation or the thermal degradation or moisture sensitivity, which is pretty much common in almost all kind of organic materials, the perovskite materials in addition has another problem, that is its intrinsic photo instability. So, when the light shines on this kind of material, we mentioned in the last class when we talk about the crystal structure, a perovskite material, for example, you take this a common perovskite CH3 NH3 lead iodide, and we say that this is a cation and this is the metal ion and this is the halogen, and we also say that this cation can move along the structure of the perovskite. So, this is called the ion migration, right. So, because of the light exposure, this Ma cation spontaneously started movement along the crystal structure, and the 3D structure spontaneously disintegrates to a 2D structure. Once we have a 2D structure, then no longer the tolerance factor ratio is preserved. So, no longer the perovskite crystal structure is preserved. If it is not preserved, so we will not get the required photophysics as we require for getting a optimum device. And that kind of instability due to the exposure of the light, that is an intrinsic properties of the perovskite. Now, once we talk about the thermal instability or once we talk about the moisture instability, there are ways to prevent that. For example, if you are too much concerned about the moisture instability, we can put a barrier layer or encapsulant, for example, a thin layer of the graphene which is almost impenetrable by the moisture layer, or any other kind of polymer layer which is highly hydrophobic. We can make an encapsulant or barrier layer on top of the perovskite to prevent it from the moisture. Or there are ways like there are thermopolymers, there are ways to prevent it from the thermal degradations also. But finally, we need to allow the light to fall on the device, because this is a solar cell. If there is no light, there is no electricity. But once the light falls on it, the device started degrading. So, then how to prevent that? So, that is one of the major reason the perovskite, although having a very large efficiency, it has not been rapidly commercialized into a product or technology. So, that is why the major research in this field has been driven to find out a balance between the stability and the efficiency. So, we want a perovskite solar cell which has a large stability as well as a moderate efficiency. So, even the 10% efficiency will do our job provided this solar cell is stable over 1 year or 2 years. So, that is done by this ion migration engineering, and it is actually you can tune the properties of the material, you can play around, like for example here you can play around with the cationic group, you can play around with this anionic group to change the morphology or compositional or elemental compositions of these devices and get different stoichiometry, different structure, a method called conformational mapping, and that gives sometimes a better stability of the devices. So, for example, instead of this methyl or Ma cation, if I use a larger cation like Fa cation, so then because of the steric hindrance those cations cannot move along the crystal structure. So, then we can arrest the ion migration probability. So, that is one way of increasing the photostability of the devices. So, there are several other aspects of it. When we will discuss about the stability of the perovskite device, we will discuss that in details. But before that, what we need to know that what are the different components and what is the role of that components in a perovskite solar cell, right. So, let us take a look of a cross section of a perovskite solar cell. Now, as I said that there is this FTO which is a fluorine doped tin oxide coated glass substrate conducting photoanode, and on top of that we put the TiO2 layer. So, titanium dioxide, mesoporous titanium dioxide, and there are this perovskite layer here, these are the perovskite layer. On top of that we put a whole transport material, for example, a conducting polymer P3HT, and on top of that we put a metal contact like gold. So, basically this is an example of NiP structure. So, what will happen, the charge carriers or the electrons and holes which will be generated here. Now, using the TiO2 perchlorate network, this electron can be rapidly transferred towards the FTO and the hole can be rapidly collected by the HTM and transferred back to the metal electrode, and this electron using an external circuit comes back to the counter electrode and completes the circuit. So, that is what we are showing here. If this is the electron, the pink color ball, so it goes to this direction, and the white color ball, the hole, that goes to the whole transport material. So, what is the role then of the whole transport material and the TiO2? So, one of the role which is obvious to us is that TiO2 grab this electron using this percolated network of the TiO2. So, the electron transfer is now facilitated. If I do not have the TiO2, still the electron can move depending upon the diffusion length of the electron, depending upon the electron mobility of the perovskite. But if I put a additional TiO2 layer, so because of the energetics, TiO2 will only allow or it will only filter out the electron to pass through it and will block the hole to leave behind. Similarly, the whole transport material, because of the energetics, they will only selectively allow the hole to transfer through them and block the electron. What is the resultant effect? We reduce the recombination. So, in addition to the weighting the FTO substrate or giving a better surface contact between the FTO and perovskite, both of this layer, both of this electron transport material and hole transport material, they also acts like a filter layer which allows one kind of charge carrier to preferentially diffuse over the other charge carrier to prevent the recombination loss. So, that is why in this kind of sandwich structure we always put a electron transport layer and hole transport layer in between the photoanode and photocathode. Now, the fabrication method of the perovskite solar cell, there are so many methods. I mean, it is important to mention that one can make perovskite solar cell either by vapor depositions method or by solution based approach. Today we will mainly discuss about solution based approach. Now in solution based approach, the advantage is that you even can make it on a flexible substrate. Now even in solution based approach, there are a lot of different possibilities are there. Today we will discuss about two commonly used techniques for the fabrication of perovskite, namely the one step coating, where you take the two different precursor CH3NH3I and lead iodide in one solution and spin coat from a mixture of them, and the two step coating, where you first coat a layer of lead iodide followed by a coating of CH3NH3I. So the two things is different. In one step method, in a beaker you take both CH3NH3I and lead iodide, let us say in a solvent DMF, you mix them together well and then you spin coat the film. In another case, and from this solvent you make the film. In the two step method, first you put the lead iodide layer and then on the top of the lead iodide layer you put this CH3NH3I precursor. So now you allow this methyl ammonium, this MA precursor to diffuse in the lead iodide structure. So the resultant morphology will be completely different if you make it by a one step method or by two step method. For example, look at this diagram of a one step coating. As we mentioned that this is a spin coater, we hold a substrate on the top, titanium dioxide layer is on the top of this substrate, and we take lead iodide and CH3NH3I in a DMA solvent and we spin coat it simultaneously the mixture of these two things, and this is called the one step coating. Whereas in the two step coating, first we spin coat a layer of lead iodide from the DMF solvent on top of the TiO2. So then on top of the lead iodide layer, which is somewhat yellowish, we put the CH3NH3I in the IPA solvent, isopropyl alcohol, and then finally we heat the substrate to get a black color CH3NH3 lead iodide. So finally we are allowing in both of the case lead iodide to react with CH3NH3I. In one case we are mixing them together and the reaction is happening simultaneously in a very rapid way. In another case we are putting the PbI2 first followed by the CH3NH3I. Now what is the difference between these two methods? We will see later on that the morphology will be completely different if we do it in two different ways. All deposition process happens at low temperature below 150 degrees Celsius, which is suitable for the fabrication of flexible solar cell based on PET substrate. Yeah. So as I mentioned that if you like to mention or if you like to fabricate a silicon solar cell on a flexible substrate, this is kind of not possible. Why? Because we have learned that the processing of silicon always involves very high temperature, but perovskite solar cell is made at a low temperature below 150 degrees Celsius. So even you have the possibility of fabricating it on a flexible substrate like PET, ITO coated PET substrate. The concentration of the CH3NH3I solution affects the crystal size from about 90 nanometer to about 700 nanometer. Photovoltaic performance was strongly influenced by CH3NH3I concentration, that is the crystal size of CH3NH3 lead iodide. CH3NH3 lead iodide degrades in humid conditions and forms lead iodide at higher temperature due to the loss of CH3NH3I. We already discussed that. So CH3NH3 lead iodide is a 3-dimensional crystal structure. If you heat it, what will happen? CH3NH3I leaves the crystal structure, leaving only lead iodide in your sample substrate, and one can experimentally prove that. So these materials are not very stable under the higher temperature. Lead compounds are very toxic and harmful to the environment, because it has been proved earlier that lead is neurotoxic and it is also nephrotoxic. So there is a possibility of leaching the lead in the environment, and that is one of the concerns for the perovskite solar cell in addition to the stability. and there are a lot of efforts have been devoted to replace the lead with some non-lead compound, for example bismuth or tin or some other combination of that. Although the efficiency number we still get very high efficiency in the case of lead based device also, but still there are a lot of ongoing research is going to replace the lead with some non-lead compound. In the next lecture, we will discuss about the structural components of the perovskite solar cell and also how the morphology can be related to the photophysics and basic introduction to the photophysics of the perovskite solar cell. Thank you very much.